Assalamu alaikum rahmatullah. Hello guys, today we will continue talking about chapter 5, machine learning basics. So today we will cover the concepts like overfitting, underfitting, regularization, about bias, variance, and the things around them. So let's get started. Okay. So in previous session we talked about learning algorithm and linear regression. And so today we will talk these key concepts. So the goal of our learning algorithm is that this algorithm should be well, should predict or perform well on the data set which are not seen. So it means, for example, if we have a model which classifies cats and dogs, and we train that model, that machine learning algorithm, and we have our model, and if I give new image, not from the dataset, not from training dataset, but new image from another place, from internet, from YouTube, I give one image to the model, and my model should work well on that image. So the ability of the model to perform well on new, previously unseen inputs is called generalization. So if our model is doing good in generalization, it means our model is doing good and it is good for production. But usually what we have is that our model works very good in training dataset, but when we give new unseen data, it performs very poor. And we call it as the model that it's not generalized well. So generalization, it's one concept you should keep in mind. And this generalization is actually, we can call it as test error or generalization error. So usually we divide our data set into several parts, like training set, validation set, and test set. And we try to split them according to some kind of metrics, maybe randomly or by just dividing certain amount of data set to the training, to test, to validation. And if we usually call test error as generalization error. When we train a model, if you remember from our previous session, we try to measure performance of model based on the training dataset. So it was like why train, right? Last time we are comparing based on the training dataset, so that our model is learning. So we call it train error. And our model should do two things, and that's very important, that the training error, the performance P, the performance measurement P should be very small. It means that make training error small. Our model should achieve that. And second thing is that the model should minimize the gap between training and test error. If you understand these two things, two sentences, then it's very easy to classify, to give definition to the terms, concepts like underfitting and overfitting. So our model should learn from experience E on the task T with improvement on its performance with measurement of P. So in that case, it should model will try to minimize the training error, the performance P error, minimize. And the second thing the model should do is that when the model is given new unseen data set, it's like test dataset, the model should perform the same as it is doing with training dataset. It's two things. If our model is doing very well on training dataset, but it is not doing very good on the second one, so that error between training and test is very huge, then it means it is overfitting. It means our model is learning too much from training, so that it is doing poor when it comes to new unseen dataset. If our model is doing poor on training, on minimizing the training error, we call it underfitting. Okay? If our model is doing poor on first one, it means underfitting. If our model is doing very not good on second one, it means overfitting. That's all. That's simply that's thing. And we say that in terms of last example, linear regression, we had the formula similar to this one, right? But we can also change this. We can also change this. We call it as capacity of the model. We can change this formula to something like by introducing the x square, or introducing x cube, or x in some degree, and introducing that things increases our model's capacity. So in book they explain that if you want to get a good, if you want to not have overfitting and not have underfitting, you should focus on the model's capacity. So if your model capacity is very huge, it tends to overfit. If the capacity is very small, it tends to underfit. So in this case, we can increase the capacity of the model. For example, our model having some underflow. If our model is having underfit problem, and we can introduce some kind of new variables to increase its capacity to learn many things, more things. If it learns more things, we will not face underfitting, so that we can get good results on minimizing the training error and having minimum difference between training error and test error. So we introduce these things. We can introduce many different kind of things to our function, and we call it, there is very good term actually. Choosing solution, input hypothesis space. Okay. So introducing this kind of things, it gives us the complexity, improves the complexity, and that's what you should know about underfitting and overfitting, and capacity of the model. So we can change the capacities. So here's a very good graph that we can clearly differentiate between what means underfitting, what means overfitting. Underfitting means that the capacity of model is very small, so that model cannot learn and minimize the training error. So here that's bad. Second one is very good, so that we introduce x square, so that it will be like a curve, and we will minimize this error, training error between them. What is overfitting then? Overfitting means that we improve the model's capacity, improve its complexity by giving another functions and more another functions, and they are doing good on training data set. Here you can see that the line cross each points, which is like training error is equal to zero. But when it comes to new unseen data set, this model in this overfitting will perform very bad in new data set. So that's what overfitting means. There's three concepts, like there is two concepts: underfitting, overfitting, and the model is always between them. So we talk about that. I think yeah, here optimal capacity is what we need, and we should minimize this training error and generalization error. Generalization error in this green line, it is test error or new unseen data. That's what it is. And this is another thing, no free lunch theorem. So it's saying that there is no ideal universal machine learning algorithm which will work for all problems. That's what it is in simple terms. And according to the book, they are saying that the goal of machine learning research is not to seek a universal learning algorithm or the absolute best learning algorithm. Instead, our goal is to understand what kind of distribution are relevant to the real world that an AI agent experiences, and what kind of machine learning algorithms perform well on data drawn from the kind of data generating distributions we care about. And everywhere in machine learning world, no free lunch theorem. We should remember about that there is no universal model which will work for all tasks. So if you have one task, one problem, and you should try different kind of machine learning algorithms, check the dataset distribution, and change the performance P and change the experience E, or do some pre-processing, so that there is no specific universal model or approach which will fit for all problems. That's what it is. And there is another thing I want to talk about, regularization. So when our model is learning, by performing a task T with respect to the performance measurement by P and with experience E, we can give some regularization so that this computer system will learn from the experience, plus with some regularization rules. So for example, this our J, which is loss function or cost function, we can introduce some kind of lambda value, and lambda, what it will do is that it will give some kind of noise or some kind of control over the weight, over the finding optimal values for weight, for parameters. And this lambda actually helps us and prevent from overfitting or underfitting, and linear regression with plus regularization, we call that as ridge regression or another regressions. And there are many different kinds of regression models, which also includes regularization. So that's all about regularization. And there is the official term definition says that regularization is any modification we make to the learning algorithm that is intended to reduce it is generalization error, but not the training error. And yes, that's all what you should know about regularization. So there are different models, and linear regression plus some regularization, it will result in new regression model which are already existing, yeah. And as we said, we can select this learning rate, we can select this regularization value and other values, and selecting this kind of values, parameters, we call these parameters as hyperparameters, and we call selecting the optimal hyperparameters as tuning. And it's very important to select hyperparameters, but this selection is done in the last step of the model. So if we select very good, if we don't select lambda, we give it 0, our model's complexity will be still the same, and it will do overfitting, assuming that if it is very complex model. If we give some kind of regularization, some control to this, some value to this lambda, our model cannot overfit, so that it will try to learn, try to find the optimum path. And then if we give a very big lambda, then it cannot learn, actually. It will just underfit. That's enough. Validation set. So validation set is that we usually divide the dataset into 3 parts, as I mentioned before: training dataset, validation dataset, and test dataset. We train on training dataset, and we check it on validation dataset. And in the end, when model is ready, when it is done training, we will check the model's performance on test set. So the test set is unseen, new set. That is what it is. We have cross-validation. Cross-validation is that we split the dataset several times. So I split the dataset, for example, we have 100 rows of dataset. I give 70 rows to training, 15 rows for validation, 15 rows for test. And I will switch it, I will change it. So first 15 I will give for test, second 15 I will give for validation, and another 70 samples I will give for training. It's second approach. So I am changing the dataset for training several times, so that the test set and validation set are also changing, so that it is so that our model is learning much more better and much more general. So this is called as cross validation, and it is usually very expensive to perform. And if you learn about scikit-learn library, they have implemented almost all of these concepts, so that it's very easy to write code on these things. And yeah, cross-validation, and we have 2 things more to cover, is that bias and variance. They are also 2 very important things. I will do my best to explain them. So there is bias for each distribution, Gaussian distribution. Then we have variance. So according to them, according to this textbook, bias and variance is explained, how can I say, is explained very good and very in details, but what generally we should understand from them is that we should have small lower bias and both low variance. So if we have high bias, it means our model is doing poor. It is not learning actually, and the training error is huge, and we are in underfitting zone. The optimal place for our model to be is here. You see here. And variance, as our model complexity grows, as our model's complexity grows, it will cause to more variance. And we need to select the optimum between these things, so that if our model's complexity grows, bias will be lower. But as it is growing, variance will be higher. If our model capacity is small, very small, it means our bias is high, but variance small. So we need to find this trade-off, like between these two things. And these two things cause to also underfitting zone. They happen in underfitting zone and overfitting zone. I think that's it. And that's, I think, clear. Okay. Yeah, to conclude, what I want to say is that you should have a clear image of overfitting, underfitting, so that these two things depends on model's capacity and not only on that thing. And there is also two another concepts like bias and variance. And when our model's capacity is very small, it will cause for big bias but small variance. When someone asks you what is optimal bias and optimal variance for the model, we should say if model is having low bias and low variance, that's the best case. And another thing, you should keep in your mind from this lecture is no free lunch theorem. So that there is no free lunch, there is no universal algorithm, there is no universal approach for all tasks in machine learning. That's it for today, guys. See you in next videos. Bye bye.